Okay, in this video we're going to look at AC circuit analysis using two different software tools. So we're going to use Octave to do a phasor analysis of an AC circuit, and then we're going to use LTspice to simulate the circuit, and we can compare the results. So I'll show you the circuit first. It's going to be an AC voltage source, which I'll represent using this symbol here. Driving current through two other branches. So we're going to have a branch which is an RC circuit, so a resistor in series with a capacitor, and then another branch which will be an RL branch, so a resistor in series with an inductor, and that's the complete circuit. When we simulate this in LTspice, we're going to explicitly ground this point here, so I might as well do that at this point. So this is going to be 0 volts in our circuit. This voltage supply here I'm going to call VS, and the properties of this are it's a sinusoidal AC supply. So it's 230 volts or MS, so that's root mean square. So the peak voltage out of this will actually be root 2 times this. But normally we would describe the magnitude or the amplitude of a sinusoidal AC source using the RMS value. So that's what I'm doing here. And it's sinusoidal AC. And I'm just going to choose 50 Hertz here. So this of course is the magnitude and frequency of the main supply here in Ireland. So what about the other components in the circuit? Well, this is going to be R1, and I'm going to make this 1 kilohertz. Sorry, excuse me, 1 kilo ohms. And then my capacitor here, what will we make this? Let's say, I'll call it C, and I'm going to give it the value 2.2 microfarads. Now for my inductance, let's make this, let me think, 50 millihenries maybe. I'm going to call this L, so that's normally the letter we would use to represent an inductance. My second resistor here, which I'm going to label R2, is going to have a smaller value than the other one, so let's make it 20 ohms. Hopefully these values will work out okay. So what we're basically going to be doing is conducting a phasor analysis of this first in Octave, and then we're going to build the circuit in LTspice and simulate its operations. We're going to do a transient analysis on it and actually see what the voltage and current waveforms look like in the simulation. So in order to do a phasor analysis, one of the first kind of things that we need to do is to convert this frequency into angular frequency, and then we're going to use that angular frequency value to calculate the impedance of each of our elements here. So in particular, the capacitor and the inductor will have impedances that depend on the frequency. So the frequency I'm going to call F, and that's 50 Hertz. So that information was provided to us here. Omega, so it looks like a lowercase w but more rounded. This is a lowercase omega from the Greek alphabet. And that's just equal to 2 pi multiplied by F. So in this case that's going to be 100 pi radians per second. So Hertz of course is cycles per second, and this is radians per second, so there's 2 pi radians in each cycle. Now before I go any further, I suppose I should say, what are we being asked to actually calculate here? So VS, this is an uppercase V here, this is the voltage phasor for the supply voltage. And what I'm going to try and calculate in this example is I'm going to calculate the current in each of these branches as a phasor. So I'll call this one IC. So it's the current phasor, the phasor that represents the current passing through the capacitor branch of the circuit. And then I'll have another phasor which I'll call IL. This is going to represent the current passing through the inductor branch of the circuit. And I suppose I might as well add in another phasor here. I'll just call this IS. So this is the current actually coming out of the voltage supply here. So this current is going to split into two and like go down the two different branches, so the sum of these two should be equal to IS. I'm also going to add in some additional voltage phasors. So I'm going to add in a phasor just across the capacitor. So it's the voltage just between the two terminals of the capacitor here, and I'm going to call that VC. So again, uppercase V, subscript C, and I will have a voltage phasor just across the inductor here. So I'll call that VL. So that's the voltage between the terminals of the inductor represented as a phasor. So each phasor that we use in the analysis that we're going to do here represents an oscillating voltage or current. But the phasor itself is just a complex number. So the magnitude of each complex valued phasor represents the magnitude of an oscillation, and then the angle of the complex number represents the phase shift of that relative to some reference phasor. So in particular, in our circuit here, we're going to designate Vs as the reference phasor. And that's really like an arbitrary decision in some ways as to which phasor you use as the reference. But in a circuit like this where there's one voltage supply, you would almost always use Vs as the reference phasor. So the reference phasor in this case is Vs, and it's just going to be equal to the RMS magnitude of the voltage. So equal to 230. Now that is strictly speaking in volts. Those will be the units of this phasor. Now, what can we say about that? Just as a sort of note about what we mean by a reference phasor, the magnitude of the reference phasor is just equal to its actual value here, because the angle of the reference phasor is just 0 radians. So it's best to think of the reference phasor as a complex number, even though, because we are actually assigning it an angle of 0, it actually is purely real. But because all of the other phasors typically are going to have values that aren't purely real, some of them are going to be imaginary, and some of them are going to be a mixture of real and imaginary, so full-blown complex numbers. So it's best to think of each of the phasors just as a complex number, even the ones that happen to have 0 real part or 0 angle. Okay, so we're going to be calculating these other complex numbers, IC, IL, VC, and VL, which represent oscillating voltages in the case of VC and VL, or oscillating currents in the case of IC and IL. And then we're also going to calculate some other things. So calculate the following phasors. So VC, IC, VL, IL. And then also calculate, so just for the capacitor branch, then I'm also going to calculate some additional values. So in particular, I'm interested in what's the peak VC, well, let's say what's VC RMS first. So that's the RMS magnitude of this voltage. Then what is the peak value of the capacitor voltage? And then we'll also calculate what is the RMS value of the capacitor current and the peak value of the capacitor current. So we'll calculate all of those things. Now, before I launch into this in Octave, I'll just remind you of a couple of useful facts that we're going to be relying on here. So I've already told you that the angular frequency is just 2 pi times the frequency in hertz. So that's one thing that we're going to need. But I'm also going to need to convert all of my circuit elements here into impedances in order to do the phasor analysis. So the impedance of each of the resistors, which I'll just write here as Z or 1, that's just going to be equal to the resistance. Similarly, Z or 2 is just going to be equal to the resistance or 2. So the impedance of a resistor is exactly the same thing as its resistance, and it doesn't change with frequency. It's a different story now for the capacitor and the inductor though, so I'll do the inductor first here. So we'll call it ZL, and the impedance of an inductor is equal to J times omega times L. So J here is the square root of -1, the imaginary unit. Omega is our angular frequency, and then L is the actual value of the inductance. So this is how you convert it into an impedance. Similarly, for the capacitor, we have a formula which is 1 over J omega C. So again, J is the square root of -1, omega is the angular frequency, and C is the capacitance in farads. Similarly, L has to be in henries. So we're going to be relying on both of those things when we do our actual phasor analysis. So I'm going to switch to Octave now, and I'll show you how to work through this one. So I'm going to fire up Octave here. Now, everything I do here will work the exact same in MATLAB. So if you're using MATLAB instead of Octave, things may appear ever so slightly different in terms of the layout of the panes on the screen, but all of the actual syntax that I'm going to use here will be the same. So just to briefly introduce you to what happens in Octave here, in the simplest case, you can just use this as an actual calculator. So for example, you can type in an expression and it will calculate the value of that expression. But you can also use variables. So for example, you could say, if we wanted to set f equal to 50, which is going to be our frequency in this case, we can just say f equals 50, and that will be stored into a variable called f. If you look on the workspace pane on the left hand side of the screen here, you can see that it's allocated memory to store that variable f, and it currently has the value 50. Similarly, if I wanted to say omega, now there is no omega key on my keyboard, so I'm just using a lowercase w because it's the nearest thing I can that I have available to me. But omega is equal to 2 pi f. So we can have an expression that includes a variable, but we also have certain mathematical constants like pi available to us. So 2 pi f is going to be calculated, and that will be stored into my variable w. Now something else to be aware of, when you type in an expression like this, by default Octave or MATLAB for that case will respond by printing out the value that it assigned into the variable. So it'll print out the answer of whatever you just calculated. Now in some cases you're just interested in storing the value, but you don't necessarily need it to be displayed on the screen. So when that's the case, you can just end your line in a semicolon and it'll suppress that printing out of the answer. So it still does the exact same calculation and it still stores the result into the variable. As you can see over here in the workspace, the number is stored in there, but it just doesn't actually print it out on the screen. This is going to be useful when we're working through a longer calculation and we just don't want it to be printing out like a load of text here which is messing up the screen. We can suppress some of the printouts just by using the semicolon. Okay, so it could work through the whole calculation here in this way, but what I'm actually going to do is I'm going to type it all into a file, and then we're going to run all of the commands in one go from the file. That means that if we want to make a change then to the calculation and repeat the entire thing from start to finish, we'll be able to just make a small edit to the file. So you could just type in the instructions here one by one and get all the way to the final answer, but instead I'm going to do it all into a file. So I'm clicking up here in the top left to open a new script. So there'll be a similar button to this in MATLAB. I can't remember what exactly it's going to be labeled, but somewhere up there there'll be a new script or new M file button, and it's opened up a blank file here that I'm going to type in all of the steps that I need to do this calculation. So in MATLAB and Octave, any lines that start with a % sign are comments, so they're going to be ignored by Octave or MATLAB. So in this case I'm going to use them to label the different sort of steps that I'm doing, the different sections in my calculation. So we'll begin by setting the frequency variables. So frequency in hertz and angular frequency in radians per second. So f equals 50. Now I'm going to put a semicolon there because I don't need it to print that back on the screen when we run our program. Omega is equal to 2 by pi by f. Similarly, I don't need it to print that out because we already know what the value is. We're assigning it to it. Okay, so that's those two. I'm going to create my reference phasor. So in this case, my reference phasor is going to be Vs. That's the supply voltage. And I'm just going to set it equal to the RMS magnitude of the supply voltage, which is 230. Okay, what other circuit elements do I have? So we've got OR1, which was equal to 1 kilohertz. So what I'm going to do here is I'm going to type this in using the following notation, 1E3. So the E3 here means times 10 to the power of 3. So in total it's going to be 1 times 10 to the power of 3, which is 1,000. The reason this is useful, especially when you're entering the values of circuit elements, is that if they're in kilo ohms or microfarads or whatever, it's going to be easier to type the number with a power of 10 after it. So, you know, and arguably it would be just as easy to type 1,000 here, but it's a good habit to get into to type it in this way, because when you get to very, very small values, such as you'd have for a capacitor, or sometimes very large values, it's going to be easier to manage them when they're written in this concise notation. So that's OR1. The capacitor value was 2.2 microfarads, so 2.2 E minus 6. So that's times 10 to the minus 6 because it's microfarads. OR2, which is the resistor in the inductor branch, was equal to just 20. And L, the inductance, was 50 millihenries. So that's 50 E minus 3. Okay, now let's calculate the impedances. So we could calculate the impedances like Z OR1, but it's just going to be equal to OR1. So rather than, you know, overcomplicate things, I'm just going to leave the resistances with their original variable names, and we're just going to worry about the capacitor and the inductor. So let's do the inductor first. So I'll call my new variable ZL. This will be the impedance of the inductor, and it's J omega L, so J times omega times L. Now a couple of things, again, that's a lowercase w that I'm using because there is no omega key on the keyboard, so this is the nearest thing. J is already recognized by Octave or MATLAB as meaning the square root of -1. So a mathematician would normally use the letter I to represent this, but in electrical engineering we're always using lowercase j for the square root of -1 so as not to confuse it with electric current. So both I and j will be recognized in Octave and in MATLAB. I've just realized that I left off my semicolons here for all of these, so I'm going to add them in just so they don't all get printed out. So ZL is equal to J omega L. ZC is going to be equal to 1 over J omega C. Put in my semicolon. So these are both going to be complex numbers. In fact, maybe it'd be a good idea if I just leave the semicolons off here. We can actually see what they get printed out as. They'll both end up being imaginary. Actually, they're going to be purely imaginary. So they'll have zero real part, but MATLAB or Octave will store them as complex numbers. So before I go any further, let's save this file. I'm just going to put it into my documents folder, and I'll just call it, what will I call it? Phasors.m. So these script files in MATLAB and in Octave are given the file extension .m. So just save that there. Now to actually run this script that I've just created, I'm going to jump back to the command window. So if you look at the bottom of the screen here, you can see I'm currently in the editor tab, but I'm going to switch back to the command window tab. And I need to make sure that I'm in the same folder where I saved that file. So up here, I'm going to set the current directory to my documents folder. Oh yeah, I'm actually already in it. So that's fine. I just need to open that folder, and you can see my current directory is now home user documents, and you can actually see my file there, phasors.m, listed in this top left pane. So to run that file, I just type phasors. So you don't need to type the .m bit, just the name of the script file without the file extension. And you can see it's carried out all the commands that I included in the file there. And the only two that actually produce any printed output are the ones that I left out, the semicolon at the end of the line. So you can see that ZL has been stored as a complex number. You can see the real part is 0. And similarly for the impedance of the capacitor, it's a complex number, but the real part is 0. And that's exactly what we expect for the impedance of a capacitor and an inductor. They're both purely imaginary. The capacitance is a negative imaginary number, and the impedance of the inductor is a positive imaginary number. All right, that's ZL on ZC. So let's add some more into our M file then to complete the calculation. So let's calculate the currents. So we're going to calculate the current phasors. So the current phasors are IC and IL, just to remind you what they were in our diagram here. It's basically the phasors that represent the oscillating current through this branch, which is IC, and then the phasor representing the oscillating current through this branch, which is IL, both complex numbers. Now the way we're going to calculate them is by adding up the total impedance in each branch, by adding together the two impedances, and then we're going to use Ohm's law together with the voltage across the branch, which we know is just equal to the supply voltage. So we'll divide the supply voltage by the total impedance, and that will tell us the current through the branch. So we'll do it for the capacitor branch first. IC, which is my current phasor in the capacitor branch, is equal to the supply voltage, which I've called Vs, divided by the total impedance of the branch. So that's R1 plus ZC. So I've added together R1, this resistance, so that's the impedance of that resistor, is the same thing as the resistance. The impedance of the capacitor we've written as ZC, so I can add together those two impedances because they're in series, and I'll get the total impedance, and then I just divide the voltage by the impedance, and that gives me the current. Just as you would if you had resistors in series, only now everything is a complex number, and all our RLC elements have become impedances. Okay, so that's IC. Let's calculate IL as well, same way. So we know the voltage across the branch is Vs, and the total impedance of the branch is R2 plus ZL. Okay, so we're making good progress. Now, the next thing we could do is we can calculate the voltage phasors across these two elements here. Once you know the current passing through them, you can just multiply the voltage by the impedance, the same way as you would if you knew the current going through a resistor. You could calculate the voltage across it by multiplying that current by the resistance. Same thing here, except that it's a current phasor being multiplied by a complex valued impedance. So that's what I'm going to do here to calculate VC. So calculate voltage phasors. So VC is equal to the current passing through the capacitor represented as a phasor multiplied by the impedance of the capacitor. Similarly, VL is equal to the current passing through it represented as a phasor passing through the inductor, that is, multiplied by the impedance of the inductor. So that's VC and VL. Now finally, what we were asked to calculate in addition to this was these four characteristics of the waveforms in the capacitor branch. So in particular, the RMS value of that voltage that appears across the capacitor, the peak amplitude of the same voltage signal, the RMS value of the current through the branch, and then the peak magnitude of the current through the branch. So I'll just show you how to calculate all of those things. Once we know the phasors, it's very straightforward to get these other things. It's just a matter of converting back from the phasor representation back to the actual time domain amplitude of these waveforms. So VC RMS is what I'm going to describe the RMS amplitude of the capacitor voltage, and it's just equal to the magnitude of that complex valued phasor VC. So to get the magnitude of a complex number, you can use the absolute value function. So it's ABS VC. Then to get the peak value of that waveform, it's going to be the RMS value multiplied by root 2. So square root of 2 multiplied by VC RMS. Similarly, to get the current magnitude, so we know the phasor representing the current passing through the capacitor. So the RMS value of that oscillating current is just going to be equal to the magnitude of the phasor. So ABS IC, and finally IC peak is going to be equal to that multiplied by square root of 2. So that's IC RMS. Right. One final comment then here. So calculate peak and RMS magnitudes of VC and IC. Now we've just done it for one branch here. You could easily do the same thing for the inductor branch, but it'd be I'd just be repeating myself at that point. So I'm just going to do it for that one branch. That's the entire calculation area. We'll just run it and check that we actually get out values that seem to make sense, and then we're going to compare it with the simulation in LTspice, and we'll see whether the values actually agree. So back to the command window. I'm just using the up arrow key to go back to my previous command, which is just the name of the M file where we've entered all this stuff in. You can see I've saved this file as well, so there's no unsaved changes here. So just say Control S to save it. There are also like buttons here on the toolbar to save it. So back to command window, run the M file, and you can see it's printing out any of the lines that we left the semicolon out at the end of the line. We get the answer printed out on screen. So for all the phasors, you can see they're coming up as complex valued phasors. So they have a magnitude and they have an angle, but they're printed out here in Cartesian form. So we see the real and imaginary part for each one. But then what we finally see down here is the RMS value of the capacitor voltage. So 189.21 volts. That's the RMS value. The peak voltage across the capacitor is 267.58 volts. And then similarly, the current is 0.13 amps. That's the RMS value, or 0.1849 is the peak current. So that's in amps. So we can refer back to these values once we've simulated the circuit to see whether these actually match up with the waveforms that we observe. So let's switch over to LTspice now, and we're going to put together the circuit and simulate it. So this is LTspice here. There's a number of different tools which are based on the original circuit simulation software called Spice. So you may have heard of PSpice, which is another very well-known one. LTspice is the one we're going to use here, and it's freely available to download. The LT, I think, originally stands for Linear Technologies, which was a semiconductor company, but I think subsequently they were bought out by Analog Devices, maybe, because I think that's who actually distributes this software now. Anyway, it's free to download. It's a great simulator. It has some kind of like quirky interface elements that feel a bit dated, but actually it's a terrific tool once you can kind of get used to those things. So first thing I'm going to do is create a new schematic from this button on the toolbar here. So what they mean by the schematic, this is basically going to be our circuit diagram, where we're going to define which elements are in the circuit, and then we're going to define some other properties for the simulation, and it'll actually generate waveforms representing what the voltages and currents look like in the circuit. So some of the common elements are available through these buttons up in the toolbar here, like resistor, capacitor, inductor, and some of the other ones are buried underneath the component sub-menu here, where you'll have to go digging around for them. So I'll just put in the resistors, capacitor and inductor first. So I just click on the resistor button, and you basically just move the mouse to a point somewhere on the schematic and click the mouse, and then I'm going to drop another one over here. So click again. Once you're finished with a particular tool, you just press the escape key to come out of it. So now I'm going to select a capacitor by clicking on the capacitor button here. And again, I'll position it on the canvas here and just click once to drop that capacitor, then press escape. Get one inductor here, so click once to drop it and then escape to get out of that tool. Now I'm going to need to put in a voltage source over here. So there is no voltage source on the toolbar here, but we can click the component button here and it will offer us a menu containing loads of different types of components that you might want to put into your circuit. So the one I want here is the voltage source element. So you can see there's the symbol of it. So select that, and I'm just going to put that over here on the right hand side. So click once and then press escape. Okay, I'm going to draw some lines then to actually connect up the terminals of these different elements here. So we use the wire tool from the toolbar here. And I think the best way to do this is I just generally tend to click every time I get to a corner to try and kind of pin down the wire. Now it will sort of like try to intelligently turn the corners with you, but I personally find it's more reliable to just click every time you want to go turn a corner with your wire. So put one in then down here. So click, 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 click. And I just need to connect up these ones in the middle here. So click, 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 click. Oh, didn't quite get that. Must have missed one of my clicks. Okay, there we go. So there's the elements all connected together in the circuit. Now, one thing I'm going to also put in here is I'm going to designate which node in this circuit is the ground node, which will be like the reference of 0 volts in the circuit. So I'm going to select the ground symbol up here on the toolbar, and I'm going to put in a ground connection just down here, and then I'll need to use a wire to connect that back to the circuit. So I'll just connect it in there. So this will be our, oops, sorry. Let's drag that back onto the screen. So this will be our reference node down here, this node here that connects the bottom of the voltage source with the capacitor and the inductor. Okay, so we're almost ready to simulate, except that I'm going to need to put in values for these elements here, and I'm also going to need to specify the properties of the voltage source. So to specify the resistances first, just right click on them and it'll pop up a box here where we can type in the properties. So that resistor there is 1 kilo ohm. Now you could type in 1000 here, but you're also allowed to use the standard prefixes. So I can just say 1k there, and you'll see it'll display the value beside the resistor. This one here is 20. Now our capacitor is in microfarads, so it's 2.2 microfarads. So there is no mu key on the keyboard, but there, you can use the lowercase u and it'll be understood as the micro prefix. So you can see it's displaying it there as 2.2 microfarads. Similarly for my inductor, that's 50 millihenries, so lowercase m for milli. So there's the 4 of those. Let's right click on the voltage source. Now by default it shows up as a DC source here, but I'm going to go into advanced and I'm going to select specifically a sine source. So this will be a sinusoidal voltage source. Now I don't need to fill in all of these things here, so I'm just going to fill in a few of them. So my DC voltage offset is just going to be 0. Now amplitude is important here, so I think I'm right in saying this is the RMS amplitude. We can check that in a minute anyway when we look at the voltage waveform. So I'm going to put in 230 and the frequency is 50 hertz. I think I can leave everything else there for now, so just click OK. If you'll see sometimes some of these labels will tend to kind of become overlapped with other things in the circuit. So you can move things around here by using the move tool here on the toolbar. Just click it to give you this access to this hand here, and then you can click and move things. I'm going to move this guy over here. Okay, so I think we're almost ready to simulate this. What will happen is basically we're still going to have to specify the type of simulation that we want. I'm just going to try clicking the run key here, and it's probably going to ask me to specify what type of simulation I want to carry out. So there are many different types of simulations that you can do in LTspice. The one that I'm going to do here is a transient simulation. So we're literally going to just switch on the voltage source at time 0 and it'll settle down after a little bit of time into a kind of a steady state behavior, and then we'll just look at the waveform a little bit after the time when the simulation started. So I'm going to set my stop time to, let's just set it to 0.5 seconds, and I'm going to say time to start saving data. Let's say, well, why don't we set it to 0 so we can actually see the transient at the beginning? I suppose no harm to see that. And I think I can leave the rest of that. So let's click OK there. And now it's actually running the simulation. So I think the simulation is complete there, but we haven't selected any waveforms yet to be displayed. So I think the first one that we're going to want to see is the actual voltage supply waveform. So you can see when you hover the mouse over your schematic now, once you've carried out the simulation, there's two different things that will appear. You can either see this kind of circular current clamp that will allow you to display the current passing through any branch in the circuit. So you can hover over an element and it'll allow you to click on it to display the current. Or if you hover over a node in the circuit, like basically the connection between any elements, it will allow you to display the voltage at that node. So I'm going to click on the node at the top of the circuit here. And you can see there's the voltage actually switching on at time 0. And we've got 500 milliseconds of the signal displayed here. Now you can zoom in on a part of this graph if you want. You just click and drag a box here and it'll zoom in on a smaller section of it. And it'll allow you to zoom in both directions. Now I'm going to go back to the default zoom here by clicking on the magnifying glass with the red X on it here up in the toolbar. And we get back to see the entire waveform. I'm going to add some more traces onto the graph. So the way they refer to each waveform here is as a trace, the same as if they were on an oscilloscope. So let's look at which one will I display next? Let's look at the voltage on the capacitor maybe. So the voltage across the capacitor, this is ground down here, so that's 0. So if I display the voltage at this node here, that's going to be the voltage basically between the two terminals of the capacitor. So you can see that waveform is lagging slightly behind the supply voltage waveform. So the peaks happen a little bit later than with the supply voltage waveform here. So that is our voltage across the capacitor. I'm going to add in a third voltage waveform here, which will be the voltage across the inductor. So I can click on that here and you can see it's put in a third waveform. That one is actually leading slightly ahead of the supply voltage waveform. So I'd like to zoom in a bit closer and see what these look like. Now it's important not to zoom in on the signals at the very start here, because you can see that it takes a little bit of time for these voltage waveforms to settle down to their steady state. If you look at the first cycle of the red waveform here, you can see it's a little bit shorter than the later ones. So I'm going to just display this from about 100 milliseconds on here. Let's look at, we'll look at about this much here. There's a few cycles of the waveform. And you can see the green waveform there is our voltage supply, and you can see that the voltage across the inductor is leading slightly ahead of it, and the voltage across the capacitor is lagging slightly behind it. And you can also see that they have different sizes. So the voltage scale is being displayed here on the left hand side. You can use cursors here as well. So if I click on, let's say I click on this waveform here, I can drag around a cursor here and I can measure things like the time delay between 2 points. So for example, if I measured like one complete cycle of my voltage supply waveform there, you can see I've got one cursor at this 0 crossing and another one at this 0 crossing. This box down here will allow us to measure the time difference between them. So you can see that the horizontal difference between cursor 1 and cursor 2 is very close to 20 milliseconds, which is exactly what we would expect for a 50 hertz waveform. And you can also use that to measure vertical distances or like relative phase shifts between different waveforms. So if I wanted to measure, for example, the phase shift between the capacitor waveform and the voltage supply, I could just position my cursors on 0 crossings of the two different waveforms and then read off the time shift between them, which we could then convert into a phase shift. So that's a very useful feature in LTspice to be able to use those cursors. Okay, so let's take a look at how the peak voltages compare with what we calculated in Octave. So firstly, we'll just take a look here and just check that we actually did correctly calculate the I now see what I put in as the amplitude for my waveform here, 230. That has actually been set as the peak value rather than the RMS value. So I'm going to have to change that. So what I'm going to do is I'm going to calculate close this for a minute. I'm going to go back and I'm going to rerun the simulation, but this time I'm going to change the amplitude here to be an RMS amplitude. So this multiplied by √2. So to do that, I'm going to use Octave to tell me the peak value. So jump back to Octave here, and I'm just going to get square root of 2 times 230. So this is what the peak voltage from the supply voltage should be, 325.27. So we can use that in LTspice to set the amplitude of our voltage source. No, that didn't work. Let me just copy that again. So it's 325.27. 325.27. Click OK, and then I'm going to rerun the simulation. So to run it, it's this little running man button on the toolbar. So when you click that, it reruns the simulation from the start. And then again, I'm going to zoom in on part of the time axis here. So just do from 50 to 100 milliseconds, say. So let's have a look at what the peak values are for the capacitor voltage. So the capacitor voltage here was, if you look down in the bottom left hand corner down here in the status bar, when I hover over that node there, you can see that it's node 3. So V brackets N003. This is down in the bottom left corner of the screen. So that is the one, if you look up here, which is being displayed with the blue waveform. So the blue waveform is my capacitor voltage. So if I click on that to select it for the cursor, then I can drag the cursor over here to find out what's the peak of that waveform there. And you can see the peak of the capacitor waveform is about 265.3 volts roughly. So now we're going to compare that to what we calculated in in Octave, and we'll see whether the values are in agreement. So this is the peak value for the capacitor, 265.3 volts approximately. So back to Octave, and you can see that our peak voltage for the capacitor was 267.58. So it's very, very similar. Probably if I'd positioned the cursor a bit more accurately there, I might have got a more precise agreement between the two, but you can see the values are very similar. Similarly, we're going to measure now the peak current, and we'll check that that's the same. So you can see that in Octave we had a peak current of about 185 milliamps, basically, so 0.185 amps. So let's have a look at that waveform here. What I'm going to do is I'm going to get rid of some of these voltage traces, and I'm going to look at the current instead. So I'm going to right click on the name of the trace up here and then say delete this trace. Right click on this one, delete this trace. So now let's display the capacitor voltage. So I click down in the schematic pane down here, then I just hover over the capacitor and click on it to display that waveform. And you can see it's the one displayed in blue here. So it's leading slightly ahead of the supply voltage waveform, and I'm interested in measuring what's the peak value here. So I'll just drag the cursor over to the peak of the current waveform, and you can see that its peak is at about, what is that, about 184 milliamps. So I think I had 185 milliamps in Octave. So very, very close. Not precisely the same, but again, probably if I position this more carefully, I might get a more accurate reading from it. But you can see anyway, it's the two calculations are broadly in agreement there. I'm trying to think what else is useful to point out here. Just if you put things onto the schematic that you need to get rid of, probably the best way to do that is using the cut tool. So you can use that to delete things. You just click on the scissors here, and then you can chop things out here. So you can click on an element to get rid of it. Hopefully I can undo that, yeah. Also, it's kind of hard to explain how the controls are for zooming in and out here, like the mouse wheel zooms in and out a bit here. But also you'll find some zoom tools here. One of the useful ones is to be able to zoom to full extent. So that's the magnifying glass with the red X on it there. That's a useful one to be aware of. Other than that, if you need to turn around a resistor or other element that you've put onto your schematic, so by default they go on vertical. If you need to spin one around, you can use the rotate tools here. So you would need to select the element, if I remember rightly. How do I do this? Move. Yeah, once you've selected it, you can rotate it and then position it where you want it. So that's what these buttons here do. You can add labels onto the schematic or onto the graph as well if you want to label things up to produce, you know, graphs to put into a report or whatever. But I won't get into that in this video. That's probably something that you can learn just by experimenting yourself. So that's probably a good place to leave it there. We've seen the basics of how to carry out a phasor analysis in Octave or MATLAB, and also how to build a simulation of a circuit in LTspice, and then how to compare the results from the two. So hopefully that's been a useful introduction.